Suppose that we are interested in the comparison between two independent populations. In these populations, we happen to know the variances of both populations, but what we want to actually do is run a test to see, are the means of the populations the same? Right? So we're in this setting where we know quite a lot about them, but we're interested in the means, and specifically, we want to be able to conduct a hypothesis test to say, do the data that we've collected actually support the understanding that these are different means, or can we fail to support that claim? So if we want to test a hypothesis regarding the difference in population means, then we can make use of a normal null distribution if we know what the variances are. So we can use Z-based testing if we know the variances of the populations here. The first thing that we'll need to clarify in order to actually conduct a hypothesis test in the multi-sample setting is, how do we specify hypotheses when there are multiple parameters? So remember, a hypothesis from a hypothesis test is going to be a statement about the distribution, which is conveyed through parameters of that distribution, supposing that that distribution has some parameters, right? So we're making a statement about the population itself, typically through the parameters of that. So if we suppose that we have two independent populations, we want to compare the means of those populations. Okay, so we can take those means to be mu x and mu y, population x versus population y. Right? Then what we can do is we can actually frame our hypothesis test as testing, is the mean of x equal to the mean of y? So is mu x equal to mu y? Right? The alternative in this case would be that mu x is not equal to mu y. So that's ultimately the hypothesis that we want to test. Now, it's going to be quite common to actually write this instead of testing with two different sort of one parameter on either side of our equality here. It's a lot more common to write mu x equal or minus mu y equals 0 versus the alternative that that difference is not 0. Right? So we put everything to do with the parameters on the left-hand side, have that equal 0. These are equivalent hypotheses. Testing one is the same as testing the other, but it's sometimes more common to think about this as sort of a difference in means on one side equals some constant on the other. Now, in a more general sense, we don't actually have to test, are these means equal? Right? We could actually test, is the difference between these means equal to some value, right? So we could say, is the difference between mu x and mu y equal to some value that we'll call delta naught here, right? So is it equal to 3? Is the difference between these means -10? Whatever we think it might be, we can plug in. That will be tested against the general alternative that the difference in those means is not equal to that value. So we can specify hypotheses that are slightly different in that sense. We can also think about specifying a hypothesis like mu x minus 2 mu y is equal to 0 versus the alternative that it's not equal to 0. And so what might this sort of modified hypothesis mean here? Well, it's useful to think about if we take mu x minus 2 mu y equals 0, right? We can rewrite this as saying that mu x is equal to 2 mu y. And if we rewrite it in that way, then what we're saying is that the mean of x is equal to twice the mean of y, or that the mean of x is twice as large as the mean of y. Right? And so in this case, you could think about running a hypothesis test like this, where we're thinking about, is the mean of x twice as large of the mean of y? Right? And so you can test the same type of hypothesis in the same framework by slightly modifying what it is that you're writing down here. Anytime that we have a hypothesis that deals with multiple parameters, we can test this in the same way as hypothesis that can be tested with single parameters, right? So as soon as you can frame a hypothesis in multiple parameters, we can turn towards the hypothesis testing framework. So we're looking for a null distribution of some test statistic that we compute that is somehow going to relate those two parameters that we know the distribution of if the null hypothesis is actually true. And then we can run through the framework of hypothesis testing from there. So what is the null distribution in the setup that we have? We're going to take x1 to xn to be from a population with a mean of mu x and a variance of sigma x squared. Independently of this, we take y1 through ym to be from a population with a mean of mu y and a variance of sigma y squared. Notice that the sample sizes for x and y can be different. So we have a sample of size n from x. We have a sample of size m from y. Right? We have the means represented by mu and then the subscript for the populations, and we are assuming that both sigma x squared and sigma y squared are actually known. They can be different values from one another, but we assume that we do know them. Now, if x and y or n and m are large enough, or if the distributions are normal to begin, the population distributions, then the differences in sample means is going to have a normal sampling distribution, right? So x bar minus y bar is going to be distributed according to a mu x minus mu y and a variance of sigma x squared over n plus sigma y squared over m. Okay. Now, if the null hypothesis is actually true, so mu x minus mu y is equal to delta naught, right? Then in theory, we could plug in the mean is going to be delta naught into our sampling distribution here. And so then that's going to allow us to actually rewrite this in standardized form, right? So we take x bar minus y bar, we subtract off the mean, which is going to be delta naught here, divide that by the standard error, so the square root of our variance term here. So that gives us our standardized version. If the null hypothesis is true, this will follow a normal 0, 1 distribution. Okay. And so that's sort of the setup that we can take here, taking this to be our test statistic that we're looking at, right? Our z-test statistic, thinking of it as a z-score in two populations, and then testing that against a normal 0, 1 null distribution. So the z-test arising here comes through our normal sampling distribution. We can use the analogous procedure to test one two-tail alternatives instead, right? So either mu x minus mu y is greater than or equal to 0, or mu x minus mu y is less than or equal to 0 against the corresponding alternatives. P-values or critical values will change correspondingly. So let's take a look at an example here. Right? We have a nursing researcher wants to compare the effectiveness of two pain relief medications. We'll call those A and B. These are for post-operative patients. The researcher knows that the population standard deviation is, they know what those standard deviations are from previous research. So they take n equals 49 patients for A, and they have an average pain score of 3.2, standard deviation of 1.5. That's a population value. Take m equals 64 for B, mean score of 2.8, population standard deviation of 1.2. Right, so the setting that we're in here, and ultimately, we want to test whether the medications produce different pain scores at alpha equals 0.01. Right, so the situation that we're in, right, we're taking n is equal to 49. We end up with x bar equals 3.2. We get sigma x is 1.5. We have m is equal to 64. We have y bar is equal to 2.8. We have sigma y is equal to 1.2. We want to work at an alpha equals a 0.01 level of significance, right? And so then the first thing that we want to do is we want to calculate our z-score here. And so in order to calculate our z-score, we need to know, well, what is the hypothesis that we're testing, right? We want to know, are these medications the same? So that's just asking, is mu x minus mu y equal 0, right? We'll test that against the alternative that mu x minus mu y is not equal to 0. Right? So then we can take our z-score as x bar minus y bar. We want to subtract off delta naught, which in our case, this is going to be 0. Right? So that's subtract off 0. Divide that by the standard error. And so here that's going to be sigma x squared over n plus sigma y squared over m. And then z will follow a standard normal if the null hypothesis is true. And we can use that in order to calculate out a p-value from the test statistic. Right? So we can actually plug in all of this information, see what result we get here. Okay. So we take all of the same information we've just pulled out here, right? We want to test mu x minus mu y is equal to 0 versus the alternative that it's not equal to 0 at alpha equals 0.01. So we plug into our test statistic here. We have our z-score is going to ultimately equal 1.5292, right? Plugging in the values that we actually have. Okay. And so from here, we want to convert our z-score into a p-value. Note that it's a two-tailed p-value, right? And so we take the probability that z is larger than the magnitude of what we observed, or plus the probability that it's less than the negative of that, right, which is 1 minus the value we plugged in plus the value that we have here. You could also write this as 2 times the negative value. Right? So that's sort of our p-value calculations for a z-test. If you actually want to compute this using R, we take p-norm of the value, and so that's p-norm of negative 1.5292, multiply that by 2, so that we can work out the exact p-value. And we find that the p-value is 0.1262. Okay. And so this is above our level of significance, and as a result, we fail to reject the null hypothesis. So we fail to reject the null hypothesis because the p-value, which is 12.62%, is greater than the level of significance of 1%. There's insufficient evidence in the data to conclude that the mean difference that we observed, which was 0.4 units, is actually significantly different from 0. And so there is no reason to conclude based on these data that there's actually a difference in means between these two different medications. We can take a look at an alternative question here. Okay, so in this setup, we're thinking about studying family wealth. They want to know how the family wealth compares across two regions, A and B. Now, from the first region, they sample 100 families, find an average family wealth of 2 million with a known standard deviation of 700,000. Second region, they sample 100 families, find an average wealth of 500,000 with a known standard deviation of 200,000. Okay. Now, here the researchers want to test whether the family wealth in region A is more than $1.25 million higher than the family wealth in B at the alpha equals 0.01 level of significance. Okay. And so what are we dealing with here? Well, it makes sense to start with our actual hypotheses that we want to test here, right? Because we are thinking about the difference in wealth between these two regions of mean wealth. So that's mu x minus mu y, right? But what we want to be testing is this actually greater than $1.25 million? Okay, so the researchers want to ask, is it greater than or equal to or greater than $1.25 million? And so the null hypothesis has to become that this is less than or equal to $1.25 million, right? Because then what we'll say is the alternative becomes that mu x minus mu y is greater than $1.25 million. Okay, and so if that's the case, right, if we are able to reject the null hypothesis, then we get evidence for this claim that the researchers are interested in testing. Okay, so other than testing a one-tailed test here, or forming a one-tailed test, we have sort of a similar situation, right? So we have n equals m equals 100. We have that x bar is going to be 2 million. We have that y bar is 500,000. We have that sigma x is 700,000. And we have that sigma y is 200,000. Right? And so then taking all of this together, along with our hypotheses, we can end up computing our z-score, right? In this case, we're going to be subtracting off this value here as the value for delta naught. Okay, and then under our null hypothesis, we'd find that our z-score is going to be distributed as a normal 0, 1. And so that's the setup. We can actually plug into this setup here all of the values and work out, well, what is the results of this hypothesis test that we have going on here. Okay, so taking the exact values out, right? We want to test the null that the difference is less than or equal to 1.25 million versus the alternative that it's greater. So we get our relevant test statistic here. Notice that we're taking our means, subtracting off. We subtract off that 1.25 million. This is delta naught under the null hypothesis. Square root of our standard error here, or the standard error, the square root of the variance that we have. And if we work this out, we get that the value that we compute for our z-score is 3.434. Okay. So we want to convert this to a p-value. It's a one-tailed p-value, right? So we just want to know, well, what is the probability that z is greater than or equal to the value we have, which is 1 minus phi of this value. If you want to convert that into an actual decimal point, we can turn towards r using p-norm in r. So we take p-norm of the value we want here, which is 3.4343, right? And if you take 1 minus this p-norm value, then that's going to give you 0.0003. So that's the value we actually want to output, right? So phi of 3.434 is this p-norm. 1 minus that gives us the p-value there of 0.0003. And so with that p-value, right, that p-value is below the 0.01 level of significance, and so then we're able to reject the null hypothesis here. Okay, so as a result, we reject the null hypothesis at alpha equals 0.01. There is sufficient evidence in the data to conclude that the first region has a mean wealth more than $1.25 million greater than the second. Right? They observe a mean difference of 1.5 million, and that is a statistically significant difference. Right? And so as a result, we can conclude that is more than $1.25 million higher family wealth in the first region versus the second. So in the event that we actually know the variances of independent populations, then we can use z-tests in order to conduct hypotheses, whether those are two-tailed, one-tailed. We can test them for equality, or we can test them for known differences. Of course, the main limitation of using z-tests in this way is that it's not going to be common for us to actually know what the variances of these populations are. And so in order to make practical use of this, we're often going to be requiring to look at alternative results in order to make use of situations where we do not know what the population variance will be.